It's a pleasure to welcome Simon Caron-Huot again to Princeton. To remember the time we were here in the postdoc. He was to talk with his title, and as always, we'll take him for dinner. Anybody who wants to join us, you're welcome. Please send me an email at 4 p.m. Make a reservation.
Okay, well, good afternoon, everyone. Pleasure to be here. So I will be talking about these two papers from last winter, not about the paper from yesterday. So we'll be talking about sort of scattering experiments that we can do from the boundary of ADS to probe the interior. And it's a bit of an old topic. And we want to do this not in purely ADS geometries, but in general geometries. But we haven't obtained any sort of spectacular result along these lines yet. We have kind of set up the formalism and set up how to actually think about these experiments, but we have not obtained a lot of results about them yet. So I thought I would start the talk by giving you a bit of context of what we actually learned from this type of tough experiments in anti-ADS, and then explain why we want to generalize this. So the first few slides will be about this context, and it doesn't matter if you don't remember everything from these slides. It's just to give you kind of a mental picture of what we're hoping to do. Okay? So if we step back to like very basics of ADS CFT, that there's actually a quite remarkable feature of empty ADS space. This is a Minkowski-Lorentzian version of it. So if you shoot a light ray on one point, then the boundary can move with the speed of light, and it takes some time to reach the antipodal point, which is just like pi times half the circumference of the thing, but it's just like pi r. And the amazing thing is that it takes exactly the same time to cut through the bulk. So you often think of the ADS space as being the inside of this kind of soup. So you might naively think that it should go faster through the middle because it's less length, but the geometry of ADS is such that it takes exactly the same amount of time. Okay. And when you think about this is a very basic consistency property of ADS CFT, because if it was faster, you would have a problem. Because you could single faster, if this interior theory is supposed to be equivalent to relativistic theory on the outside, you would violate causality on the outside. So it better not happen, and ADS CFT thankfully passed that test. But yeah, in CFT it's a very basic theorem, but in the bulk it's telling you something that is very non-trivial. It means that in this bulk theory of gravity, to the extent that there's local physics in it and we can think about it, then it means that this physics does not allow faster than light signaling. And okay, this is related to, in classical physics, in classical geometry relativity is related to the Caron-Huot theorem, which is related to having the null energy condition and energy properties like that. But it's a true property of the quantum. It's an exact statement on the CFT, and therefore it's an exact statement about the bulk. And it's a very remarkable statement when you think about quantum gravity, because the metric in the inside is supposed to be always fluctuating and so on. There'll be some metrics in the path integral where you can go faster than light, but somehow these metrics would cancel out in the path integral, and like causality would be respected exactly. So it's a really amazing statement that gravity managed to preserve this speed of light concept despite the fluctuating metric.
But if you try to do holography at finite cutoff, then there is
but then you're not talking about the CFT at the boundary.
Yeah.
So a continuum field theory at the boundary. But then the violation, you can debate whether they're really coming from intrinsic gravity thing or just your dimension of the boundary. But so what we want to do is various tough experiments in the bulk that exploit this. And instead of just looking at one geodesic going from 2 to 3, we can do some slightly more interesting things and look at a particle going from 2 to 3 in the presence of some other excitations. All of that embedded in all of that small perturbations of anti-ADS. And on the boundary, if you think about this configuration, 2 and 3 are space-like from each other. The combinator must vanish. So we have this coordinate at the top. And if you insert a complete basis of states in the middle, that in conformal field theory, that's the orbital product expansion, it gives you this famous crossing formula that just the equality of the two terms in the computator is the crossing equation, CFT bootstrap. And what we started doing a few years ago was trying to manipulate these equations to learn not just about, learn a lot of general things about CFT, but wanted to learn specifically about the local physics in the bulk. What we've done is that we integrated this crossing equation against some bars Fourier-like transform of the boundary to localize it such that it's actually probing a neighborhood of a scattering point in the middle, a region that is smaller than the ADS regions. So you're probing some kind of, so we can use this type of tough experiments to probe local physics in the bulk. If theory is suited, if you're in an orographic theory, that's suitably as local physics. Okay, that's the usual large M, large gap assumptions. And what we found by this thing, by doing this, playing this game of doing integral transforms, that when you apply the right transform on this conformal blocks, these conformal blocks are a relatively complicated function, but you apply the right transform to it, and it just becomes spherical harmonics, and this some rules just becomes what we call dispersion relations in S matrix state when acting on AV states. Okay, so the contribution of AV states here is exactly the same as if it was like a particle in flat space. It propagates a small amount, a small distance from A to B inside this circle.
Do you need to use the theory of photographic to have the last two lines?
Yeah, the place where it's used is that the relation holds for the exchange operator that have a large dimension. And specifically, actually, these things kill this kind of combinator square thing that kills all the double trace. So what enters in the sum are the single traces with large dimensions. So these behave like particles. The place where orography, the fact where the large gap is important is that you cannot treat the low-lying operators in this way. But in the orographic theory, there's very few low-lying operators, so you can treat them explicitly and separately. So yeah, this statement is just kinematical, but in order for it to be useful, you need a theory to mostly have operators with large delta. So motivated by this relation, well, then this becomes a question of analyzing what can we prove using. So this is not the goal then is not to get the most general CFT bootstrap constraint, but just let's analyze those we can get on these local processes by studying S matrix of gravitons, which is technically much simpler than analyzing stress tensor collectors. And then there's something that are actually quite special when you think about the scattering amplitude involving gravitons. So what do these sum rules give? So I was saying that this type of bootstrap equation, typically what you do is you take the low energy. Typically what happens is that the terms with small dimension on one side balance against the heavy operators on the other side. So we have similar sum rules like this in S matrix theory. And what you get is that graviton exchange is related to sum over all heavy states. There's something slightly interesting that happens that I won't be able to, I'm just trying to highlight the result without explaining all the details. It's only the high spin operators and heavy that matters in the sum. So basically you can write G Newton as a sum of positive things using this technology. And
Sorry, yeah, why is there a square?
it's a square because in the context of this matrix theory, it's because you get in the Cyber-Kramers-Kronig relation, you're expressing M as an integral of its imaginary part. And the imaginary part is related to M squared by unitarity. Thanks for the question. So end up with the important thing is that you don't quite know what these things are. There's sum over all various random heavy couplings, pseudo random, but they're positive, and that's all that matters in this discussion because they're positive. Well, G Newton is a sum of positive things. And that is amazing because we discovered that gravity has to be attractive. Okay, that's the starting point of this. And what's special about gravity is that you can make these arguments, these are kind of dispersive arguments that take quite some time. These arguments are really about things which grow with energy. Gravity, like you think about gravity as like GMM over R squared, that's the force. But when you're scattering things that go fast, it's not the mass, it's the energy that feeds gravity. And because the gravity force goes with energy, any force that goes with energy has to be attractive. That's what we learn by this type of arguments. Okay? Doesn't apply to QED because it doesn't go with energy the same way. So electromagnetism can be attractive or repulsive, but gravity goes with energy and has to be universally attractive. Great, but okay, Newton knew that. But when you look at this sum rule, what is really interesting, what we find really interesting about this sum rule is you look at it the other side. You make a statement about the IR, you measure Newton's constant from some long distance process. And what this tells you is that there's a finite budget. G Newtons give you a finite budget for how graviton can couple to anything. And because there's a finite budget, you can bound any correction to GR. So if all the terms in the sum have mass above some cutoff, the lightest spin-4 particle, then all the terms in the sum, you look at higher derivative correction, they'll be suppressed by powers of 1 over the mass that's run in the sum. And therefore, you can dominate one sum in terms of the other. And you learn that the corrections to any higher derivative correction to Newton's gravity must be tied numerically to the mass of higher spin particles. So these arguments go.
So sorry, when you have corrections, do you have an extra term in the left-hand side or?
Yeah, the way that the correction work is exactly, you're looking at a different part of low energy, basically taking more derivative with respect to momentum transfer. And that brings inverse power of the mass of the right-hand side. Yeah, so you get basically sum over the same unknown, but weighted differently by power of the mass that respects dimensionalities. And this is something that's a bit surprising. So all of these tough experiments, I want to emphasize, they proceed way below Planck energies when gravity is still weak. It's not about unitary variation. It's not about the fact that gravity varies unitarity at higher energies. It's already at low energies. If you had a correction to relativity, if you had a correction to GR, as soon as this correction competes with R, there has to be higher spin particles. Even if the amplitudes are all small. It's only for gravity that you can make arguments like this. Yeah, so some quantitative results were obtained along these lines. So we apply this in deep flat space dimensions. We get bound like this on the quotient Riemann square, and we get this bound have been proposed parametrically by other people before, and we get actual numbers in these bounds. In the context of ADS-CFT, the Riemann square coefficient tells you something about the center charge of the CFT4, tells you that if they are so-called two-center charge in 4 dimensions, they have to be very close to each other if you're in this so-called theory. And the important parameter in these sum rules is the mass of the first higher spin particle. I call it significant. We can call it an elementary particle. There's a very natural concept of being a particle being elementary or composite in this context. It has to decay strongly to 2 gravitons. So like the world is full of spin-4 states, like positronium bound states. It's kind of any spin can decay, but that positronium is not an interesting spin-4 particle for this purpose because its decay to 2 graviton is like suppressed by electron mass over m Planck compared to what you need. So first, you need the elementary, so you need something that couples like the spinning states of string theory, that couples very strongly to gravity. The mass of that first state is what controls that.
I guess those other states would contribute to this, but they have additional oppression. You don't get this.
Exactly, they contribute with a negligible amount to all of that. Yeah. So the precise statement is that if you give me a value of the correction to lambda, I can tell you that the integrated spectral density of spin-4 particles need to exceed some number up to a scale that's related to lambda. So yeah, and all the things you can calculate, like positronium pairs or spinning strings in QCD, all of these things, they contribute a negligible amount to the sum. So, and maybe I will briefly comment on some other work with Joe. But it seems that, this type of higher spin state that contributes to some rules, it's really impossible to have them by thinking about QFT coupled to gravity. If you think about particles interacting with each other, you never get that. So really something new has to have this higher spin elementary particle, like a spin-4 elementary particle. Who heard of that? Like it's a fundamentally new gadget. It's some It's something that exists in like string theory or it doesn't exist in physics. And when you add it, we believe it really signals that space-time is breaking down and something new is taking. But so I could spend a whole hour discussing more of these ideas and ways that we're hoping to constrain more of these higher spin particles and so on. But that's not this talk. It was just to give some context to what what we achieved in ADS by thinking about scattering experiments in ADS. And so why would we want to do this in like non-ADS? Any questions? Probably a lot of other questions, but yeah. What I've said so far, we'll not have to remember it for this. So why do we want to do this in non-ADS geometry? Well, it'd be nice to do something like a CFT bootstrap in a non-conformal field theory, and people are trying to bootstrap QCD, so it's great. But if you think about local operators in a theory that's not conformal, one great thing about 4-point function in CFTs is that they're a function of just two variables because of all the symmetries. In two variables, it fits in people's brain. That's great. You can draw a plane and think about it. And like correlation function without the symmetry, they're a function of like 6 variables. People are scared by that, and so it's just basically it's just interesting to look at in for example, using holography or models. There are interesting corners of the space that are worth studying. So you can start somewhere. Okay. Also, it's interesting to study holographics, even CFTs, but maybe in excited states. So like 2 different ways you can get a non-ADS geometry is if the theory is not conformal or the state is not conformal. So these are both interesting things. The other thing I think there's the main motivation, I guess, probably for this talk is that, okay, let's just ask for fun. Like, suppose like we have the holographic system, like how would you actually do an experiment that tells you like the geometry inside? How would you actually do it? Just think about that. And more abstractly, we like to understand like how geometry emerge from a system that just is strongly interacting on a system. Okay. So I'll tell you the type of tough experiments that we actually studied in this work. It's funny, there's a cursor here and not on my screen. Is that not your screen? Yeah. Okay, yeah, so that's the problem. So I described some simple tough experiments that we talked about. I've described them quantitatively, and then I described the actual calculations. The really key part is kind of a nice exercise, but I'll probably be able to go quickly through it. And describe how we actually learn from it. So the experiment will let's assume we're in the future and like some very clever experimentalists managed to create an holographic system in 2+1 dimension. And like they hung it up on this wall, and like it's this screen. Like, this screen is like a strongly interacting 2+1D CFT. It's been done. Okay. What we'll do with it? Well, so presumably this CFT will be made from electrons or something. So there'll be some operator in the CFT that couples to our electron. So there'll be some operator in the action that go like this that couples our electron to a field on the CFT, right? So that means that if you throw an electron at the screen, there's a chance that it reflects, and there's a chance that it actually enters the system on the sheet, right? So what happens if it enters? So basically the calculation of, there's a calculation of what happens when you insert a local operator in the CFT. It's been described. And what happens is we basically create a shell of energy, spherical shell that expands at the speed of light. Whatever is the effective speed of light inside the sheet, it will expand out outside. Okay. And in the CFT, we have 2 different ways of looking at the same picture. We can say, okay, on the CFT, there's just this shell of energy that's expanding. But we can also say, which is like a point particle, this is our electron enter into the space. It's like behind the screen, right? Just imagine the ADS space is like behind the screen. And the idea is that, like, the point is that these 2 descriptions are equivalent. You can either say this is a shell of energy expanding on the boundary, or if this particle is a point that's going deeper, and the depth maps to the radius, the size of the thing. Okay? two viewpoints are equivalent. But okay, at this level, it's just two ways of looking at the same thing. But it really acquires juice when you do more interesting experiments. Like if you send in two particles sideways, send electron from here, electron from here, and they can scatter in the bulk. If you think about this sort of scattering process, there's a chance that one particle comes back, and okay, by momentum conservation, the other will keep going into this space. But one will come out. And this would be a very crazy thing to see, because all the energy is very far. You have this shell of energy that are like very, very far, and then all of a sudden it's like a particle is like coming out of nowhere in the middle. So if you actually could realize a holographic system and you would see this, like this would be just amazing. It's amazing that the quantum system could do that. Okay. But the point of today is that okay, we're going to try to do that type of scattering experiments to learn about the metric inside and see what it does. Okay? These experiments are very similar to experiments we use in MTADS to constrain the bulk theory itself. Now I want to use these arguments to constrain the geometry.
That's a clarifying question. So here your holographic system is realized on a brain.
Yes.
Like a higher, in a bigger space, and then you're saying that that brain is moved.
Yeah, exactly. So this is not necessarily the ambient space is not necessarily the flat space that will surround the brain in string theory. It doesn't have to be that. So I'm abstracting. So in the DSCFT, there's a near horizon region near the brain, and it maps to some flat space region. Yeah, I'm cutting off that flat space region and just coupling the brain to us. And because the brain, because I'm just coupling the CFT to us. I'm not thinking of the CFT as coming from a brain. I'm just thinking of it as a field theory that we can couple to.
But it's in a brain sitting in our space, right? The CFT. It's a lower dimensional CFT sitting in a brain.
I don't know if I would call it brain. You know, it would be like a stack of electrons, right?
It's the system that is simulating
The system would be simulating a brain, but I really think of it as a CFT, not as an actual brain in string theory.
You're saying it's not fundamental? That's
Well, if they give the same CFT, you wouldn't be able to tell one from the other. But the region outside the brain doesn't have to have anything to do with string theory. Yeah. By the way, it's very intriguing to think about how energy conservation works in this sort of phenomenon, because this particle like looks like it's coming out of nowhere. All the energy is like far out, and then this particle comes in. So how the hell is that possible? And I think the resolution is that this sort of energy that we're showing as a shell is a small coherent part of a huge background of fluctuating energy. So if you look at the energy density, if you look at on the CFT, you take the energy in some region of size R, and you take its R inverse fluctuation, there's going to be a multiple of H bar over the size of the region times n, where n is basically the center charge in the TT 2-point function. And it's important for this phenomenon to work that this n is large, which means that this signal is like happening. You have a lot of energy floating around. And what is happening is just that some of the energy is suddenly becoming coherent and expelling a particle, but the energy was there all along. So you can only, and now how much energy you can concentrate in a small region compared to where you started from is related to. So you really need a large TT 2-point function in order to have any hope of observing this.
okay. That's another clarifying question. So the particles in the ADS description, particles in the ADS throat are the same particles as the space outside?
No. I mean,
Because the intuition you gave was that the particles.
yeah. I mean, okay. It doesn't have to have the same. It doesn't have to have the same property. So our electron is coupled to the CFT operator, which is coupled to some bulk field, which you could call psi E prime. The E prime has a different mass, it exists in a different geometry. It doesn't have this bulk field that's dual to that. You could call it the bulk version of the electron, but it's not really our electron. Yeah, thanks for that. This is a slide that I don't want to come out overly critical, but I felt I needed a slide to explain like why isn't that this solved like 30 years ago, 20 years ago? And there's a lot of things that go under the name of reconstruction. The simplest thing that is known is that if I give you, for example, the expectation value of the stress times for all times in the boundary, you could in principle integrate the equation of motion radially to learn about the bulk geometry. And I just want to make a point that to me, this is not a satisfactory way of thinking about local physics in the bulk. And the basic reason is that radial evolution is not like time evolution. It's like it's numerically unstable. It's like solving a diffusion equation backward. And it's easy to see why. It's because if you're allowing the possibility that your bulk state contains some particle that is localized in the bulk, and if you don't have access to all the boundary, just a subregion of the boundary, there's a possibility that, suppose you're trying to reconstruct the bulk field at X. So you're trying to pretend you're measuring the field at X, but by doing measurement on the boundary. Well, this particle has a wave function which is exponentially small at the boundary. How small it is depends on its energy and the distance to the boundary. And so you have to work from so this somehow this exponentially small signal at the boundary has to become an order 1 signal at X. So it's not a very, so the signal to noise ratio is exponentially small when you're trying to reconstruct local physics with this type of radial evolution. This is something that's been discussed by many people. And however, and the basic point is that in order to do the tough experiment that I was describing in the beginning from consistencies or 4-point functions, I need a signal that's order 1. Like I cannot do anything interesting with an exponentially small signal. So this already is a non-starter. But actually there was a nice paper a few months ago which says that this discussion is pointless because this reconstruction does not exist. And I think this argument is correct. The argument goes as follows. I don't think it's widely appreciated, but important to recall it, to describe it here, is that once you have interaction in the bulk, suppose you allow the possibility that you have bulk states which have other particles that could interfere with your measurement. So you have particle here coming in and it's hitting the thing you're trying to measure. Clearly, this is going to affect your measurement. The HKLL came up with a very nice procedure that says that, well, if you have small interactions that can perturb your measurement, well, if you're able to control the environment for the thing that causes it, then you will be able to correct the formula and account for it. And that works perfectly if you have access to the whole, if you surround the whole system. You can detect, you can correct for anything. But if you only have access to a part of the boundary, then your ability, if the effect of this perturbation is bigger than your ability to correct for it, then it just doesn't help. The correction, the series of correction is
not easy to do. I mean, in principle, if entanglement wedge reconstruction is corrected, it should be possible.
Yeah, so I think the bigger point is entanglement wedge reconstruction is not HKL at all. So yeah, I think there's an important point that we often hear. So what one I think was describing is that we often hear the shortcut that there's this thing called entanglement wedge reconstruction, which purpose to solve this problem, and people sometimes affirm that when you apply entanglement wedge reconstruction to an operator inside the causal wedge, it reduces to the HKL form. I think this is inaccurate. I believe I think that if entanglement wedge reconstruction is actually correct, my opinion is that it will have to be using gravity in some way, even in the causal wedge. I think this is what this estimates show. So this is something that should be clarified there. Yeah, so I wanted to spend a bit of time on this. So what I would try to do in this talk is not to reconstruct in that sense here, but I would be happy to, like the simplest way you could do something that's like a measurement of the field at X. It's like you send in an electron and you ask like, will this photon reflect on it and measure the reflection? This is not the same as measuring the field of X because this is like measuring the electric field at X in the presence of the perturbing electron. It's a slightly different question, but it's one that's much more straightforward to ask, and that's a question that we discuss. So we'll discuss a different question where I'm happy to disturb the system.
Clarification question for point number 2.
Yeah.
You're imagining that the interaction happens sort of in the past, to the past of the causal wedge. Is that the idea?
It could be even inside. Could be inside because in terms of HKL, you'd be trying to basically in order to correct for this interaction the point is that none of these particles is headed to the boundary. None of this particle hits the boundary in the region you're measuring. So your ability to correct for them is in terms of HKL, you basically just have to wait for it to tunnel the boundary. You have to repeat your experiments many, many times until you're lucky and the particle tunnels from here to the boundary. But the problem, if you don't have interactions, you can do this by repeating the experiment many times. But the problem is that if you have interaction and the interactions are too strong, repeating many times will not help you. If you get the effect of the thing is bigger than your ability to control for it. But the experiments, the tough experiments I will discuss, they have order 1 signal to noise ratio, and they just aim to do something different. Okay. So compared to previous discussion, the so-called bulk point singularities, the main thing we'll do is that we'll make sure to introduce directional wave packets. This was actually discussed in earlier paper on this by Poshinsky. And there's a big advantage to trying to probe local physics in terms of directional wave packets. So basically, we'll just do some Fourier transform with Gaussian wave packets at the boundary. But the point is that to start with well-defined position and direction, it's a bit better because if you start from if you shoot from points and you imagine sending spherical waves into the bulk from points, in order to isolate one bulk point, if the bulk is like 5-dimensional, you need at least like 5 points. But actually, in order to see that something happened, you need a 6 points to control for it. So you need these very high point correlations. And what I find is when you start talking to people and tell them about this beautiful tough experiment that uses a 6-point correlator, they stop listening. So we have to do something simpler with 4 points. But with 4 points and directions, it's actually very easy because if you basically just from the data of one of these operators, you single out one library in the bulk. And then if you shoot a second library, almost all the time they will miss. So just by scanning over the shooting angle here, you already learn a lot about where that point is. And then you look at the things that come out and it will really tell you that it came from one point. But just to isolate one point, you need one shooting point, one shooting angle, and then you shoot a spherical away from the other point, and that's enough to single out a unique bulk point. Okay? So it's much easier to single out point, and then the rest are just like redundant information. So that's a very simple idea, but it's good to use wave packets. So the basic geometry of the bulk in this case, so given any bulk point, the star of the problem is its past and future light cone. Where do they intersect the boundary? That's where you get the signal. I'm going to be focusing on massless particles in the bulk, they move at the speed of light. So the signal, where you shoot to reach it is this past. We call it hyperbolic because in general it's like past light cone hyperbola. It looks like a circle, double ADS. And so this past and future one. And yeah, that basically that as you vary the point X, this data changes, and this data tells you everything about the conformal geometry of the bulk. In fact, it's been discussed a few years ago how to extract the conformal metric with dust, and we'll describe a very concrete implementation of that. So yeah, from the shape of these hyperboloids, you can really read off the bulk metric, conformal metric. The other ingredient is a bit more subtle, that we want to do something like an inclusive correlation function. So remember the basic situation I started this discussion with was like this system on the sheet. did the scattering experiment, and by momentum conservation, they could have one particle come out, but then the other has to fall in. You can't recover all of the ones. In global ADS, you can recover, but in many situations, like Poincare ADS, you cannot hope to recover all the final states of your scattering process. But still, you can do experiments. And actually, another situation that's an issue is if you have imagine a spherical Schwarzschild black hole inside of the bulk, it would be some smaller cylinder inside the big one. As soon as you go inside the photon sphere, if all the radial momenta you have to be incoming, and therefore by momentum conservation, you can't recover everything. At least one of the guys will have to be falling into the black hole. So there's some momentum conservation impose some like, let's say like arcane, but like difficult to like characterize, quantify constraints on like what point you can probe and what point you can't. But basically it would be much better if we don't have to worry about this constraint. And the solution is simple. You just do like we do with colliders. We just accept to miss some particles and try to extract information from the thing we do see. This is called inclusive measurements. So mathematically, what does that mean? This is head. So just as a simple mathematical model of it, inclusive measurement. Let's imagine you have a tree, and you're trying to see it by watching sunlight reflect on it. So here's some kind of operator which creates sunlight, or some kind of current state of light. Actually, let's send laser light. It's easier if it's current. So yeah, that will send a current state of light, and then you measure the electromagnetic field after it's reflected of the tree, and that's like one. We can model this as a one-point function that absorbs the photon in that state. And when you take the expectation value in the state, mostly the A and A daggers commute past each other except for one. So it's basically a 4-point function that looks like that. Okay, so it's a 4-point function which describes the electric field of a laser that's reflected off the tree. Okay? And the important thing is that it's not a time order correlator. Just because I took a wave function and its complex conjugate, so both of the trees are early. One of the photon is created early, and then the one I'm measuring is late. It's not a time order thing. It's also not what people call OTOC. It's not like late, early, late, early. It's just early, early, late, early, but it's not time order. Okay? So this type of in correlation functions is a straightforward way of basically, in terms of the physics of the tree, this is a very natural thing to do because it means you can do this measurement. You can measure the light that's reflected out of the tree without having to specify the final state of the tree, which is great because the tree is too complicated for me. So it doesn't fix the microstate of the tree. It fixes the initial state of the tree, but this measurement will be largely insensitive to it as long as the same microstate on both sides. Yeah. And you could average over that. So in various notations, the thing we're studying looks like that. So it's a non-time order product, early, early, late, early. You could try to write it in terms of, you can insert a complete basis of late states. You can think of it as some kind of amplitude to two things going to two other things, and then this other thing going backward in time. And if you do this, you get this picture on the right. So this dashed line is where I insert a complete basis of states. And you see, I have a 2 to 2 amplitude. As I made 3 of my light, the scatter, the light scatter. That's the light I'm going to emerge. This tree keeps evolving, but then I multiply this final state of the tree with just the tree evolving on its own. And that's like adding this light blue line in the back. Okay? So just like the kit and the bra get multiplied together on this dash line. Okay? You can also do this in terms of Schwinger-Keldysh time fold, or to call that is familiar from Indian calculations. Okay? So technically, that type of yeah, and the reason we study that things instead of time order amplitude is really in order to be able to say anything about situation like Poincare ADS, where you lose some particles. So this model like sending out a spacecraft and bouncing like a bit. This simple tough It's a very simple experiment that's modeled by that. And as I went to in physics, like you get the information even like if you don't recover the spacecraft. It's like it's like we learn right now about the geometry of the solar system by communicating with the Pioneer spacecraft. Like we don't have to go back and get the spacecraft to get the information. Right? Just getting the reflected light is enough. Right? So that's the philosophy of this experiment. Should be a basic experiment. Sorry, this is not try anymore. It's not working.
It's an analog pointer up there.
Okay. So yeah, so I'll tell you a bit quickly about it. Technically, how we think about doing this. So basically, we consider wave packets that have high enough energy that are going to be able to use WKB in the bulk, the general geometry in the bulk. So we assume the geometry is smooth enough that you can do WKB. So some smooth background geometry may not be ADS, and we add particles moving on top of it. And we're going to neglect interactions between these particles until they get close to each other. Assume all these particles are of like wave function that's very localized. And there's going to neglect long run forces, which is not quite correct, but let's do that. And we're going to treat the region in which they actually overlap with each other as flat. Okay, so they all focus so that they reach they interact in the region that's smaller than ADS. So it's going to be basically some flat space amplitude near X that captures the process. Okay. So let's discuss the wave packet. So there's just like Gaussians, very simple. And if you put the Gaussian with that's peaked around some positive time-like energy, it's going to create some particle. And so it has definite energy, momentum, and starting point. How do you get the bulk wave function? Well, the bulk wave function you define as follows. You take this boundary operator and this bulk, so it's like a boundary to bulk propagator. And in physics is the following. So deep in the bulk, you have some WKB expansion, approximation because of the high frequency compared to the bulk geometry. But near very close to the boundary, this breaks down and you have to use some exact solutions. I'm going to assume that close to the boundary, this region is ADS, so I have an asymptotically ADS spacetime. This is just so I can actually treat this non-WKB region. And this is some kind of Bessel function that is known and standard, and then it's going to merge to the WKB region in the bulk. That's how we calculate this bulk to boundary operator. So this is the wave equation in the bulk. And okay, you can think of it as being calculated from quantum mechanics single particle path integral. So what's the star of this is the action in this one particle quantum mechanics. That's what's going to tell us the phase of this amplitude in the bulk. So this is the action of a particle written in a form that has a smooth massless limit. And then the phase of wave function is the Hamilton-Jacobi function, which in general classical mechanics is a function of the two endpoints. So basically you take position or momentum at each of the endpoints. You have a function of that. And the derivative of that Hamilton-Jacobi function with respect to x gives you the momentum. Okay. You actually calculate it, and it is actually what you would call the momentum. So if you have close the boundary, you have at least locally a translation symmetry. What I call the momentum coincides with the Noether charge from translations. But deep in the bulk, where I don't have the symmetry, momentum is just defined from this action to be this. But it satisfies always this mass shell condition. What we found is that this action, that's a function of two endpoints, is not useful. And actually for massless particle, it's very weird because it's only defined when the 2 points are light or null from each other. Otherwise, there's no geodesic that connect them. So it's a function that's only defined in some cases, and when it's defined, it's identically zero. So it's not a very interesting function. The thing that is actually useful is its Legend transform. And this is a problem this is a function that actually is surprisingly nice and useful. We fix the boundary momentum, the momentum that's tangent at the boundary, and a bulk point. I will draw it in a minute. Okay? The procedure is you fix a bulk point, you shoot from it in various directions, and then you ask, where do we end up the boundary with the correct tangent momentum at the boundary? And that unit generically uniquely fixes a geodesic. And it's a non-trivial function in a massive case. And it also works in a massive case. Massive case is a bit weird because the time-like geodesics don't reach the boundary with the S. But there's still a quantum tunneling that happens, and there's a complex geodesic that reaches the boundary, and if you apply these formulas to a complex geodesic, it all works. Okay. So here's the picture. So the data is a bulk point, and momentum at the boundary, which is like the direction you shoot at the boundary. So I fix the bulk point, and an angle at the boundary is going to be a unique geodesic that connects them generically. This function contains everything you want to know about the problem. So if you take its derivative with respect to P, it gives you the position on the boundary that you hit. So, sorry, derivative of the action with respect to P is X. So basically, by taking a derivative of this function, you get this, you trace this whole curve. You vary the boundary P, and you trace this whole curve. So the whole shape of this future-like cone is contained in this function.
For massless particles, it's just P dot X because you said the
Yeah, exactly.
comma X was 0, right?
Exactly. So to be the same as P dot X, exactly. So it's a P dot X and that's why then the derivative with respect to P give you X. Yeah. But even for massive, it's always give you X. Yes. And the other thing is you can take a derivative with respect to the bulk point. And then the derivative with respect to the bulk point just tell you the bulk moment. So everything you could possibly want to know about the scattering problem is contained in this function of two variables. Boundary momentum and bulk point. So that's a nice gadget. And in fact, even more when you study the so the exact ansat for the boundary wave function up to correction are suppressed by 1 over P. So there's the exponential reaction, and then there's the one loop determinant, which actually can be expressed explicitly as a derivative in terms of the derivative of S, the second derivative of S to do this factor. Like determinant. So really, all the information you need is in this function.
So you are doing this saddle point for the path integral.
Yeah.
So you're using H bar as like 1 over the frequency
Yeah.
of the waveform.
Exactly. Because taking E S of H bar, but the action goes like frequencies, so exactly. So large frequencies like small H bar.
For the action, you're always taking the free particle action? Or it could be
Yeah.
some generic?
Yeah, so we studied this. So the idea of this is that this actually is a solution of the wave equation in the bulk. And you can generalize this, for example, to spinning particles. Then you get some extra factor in front, but this part will stay the same. Basically, the polarization of particle gets parallel transport into the bulk. That's basically all you have to know about. So yeah, so basically, then the question of computing 4-point function of these processes is yeah. So what we basically do is that we have this WKB function that started from here and going to the bulk, and near the bulk point we approximate it as a plane wave with momentum x. Some optical limitation, like if you have a bulk that's a bit too crazy and geodesics focus and things like this would break down. We'll discuss some examples of that, but in the generic case, this works. And so basically, what we do is that we turn the wave packet, the Gaussian wave packet in the boundary, into a Gaussian wave packet in this flat space region, and then study the scattering of Gaussian wave packets in flat space. That's basically our answer for the 4-point function in this thing. Okay. 4-point function with operators when they aim to miss each other. And there's a whole bunch of factors in this. I want to explain all the physics in this thing. So for example, if the singular would be small if maybe they're not aimed at each other. So you see all of this come out of these formulas, like if the Gaussian wave packets are misaimed, you just get like a small answer. On the other hand, the other thing that can happen is that they're perfectly aimed, but one of them has too much energy, so momentum is not conserved at this interaction point. So there's also a suppression if you violate momentum conservation in the bulk. So all of that come out of the scattering of Gaussians. And okay, we'll skip this. So yeah, you can do this for non-time order, like the inclusive things I described. The basic picture is that you have 4 time operators. Every time you have a particle in the bulk, you have an operator that creates it, another that absorbs it, but you can do this from the future or from the past. You have always four types of operators, and this maps to in and out creation and deletion operators and scattering theory. So this nicely map each other. And basically, by extending Schrödinger addition to the bulk, you just keep the same operator ordering in bulk and boundary. So let me show what we get from this type of thing. So if you apply this to empty ADS, in the kinematics that look like that. So I send, this is very similar to the experiment I described before. You send it 2 electrons sideways, 1 and 2, and then you measure one going back, and you, oh, sorry, it's not like the experiment, it's a different experiment than the one I described. I'm trying to, computing an interference between these 2 particles and one that would be shot like this. Okay? So if you have a current state, the superposition of these 2 things, the interference between them, I measure the 1-point function of the field in the future, and I'm tracing the place in the future where this 1-point function is large. And the question is, can you actually like measure this future Lycone of X by doing these experiments? And here's the type of things you get. So really just, this is the magnitude of the 1-point function of O in the state, and you just see it's a nice sharp hyperbola. And this is really amazing because it's this signal is, you see this is time up. So basically the signal is happening simultaneously at different points in space. So it's not like created dynamically inside the boundary. It really has to come with the bulk in order to look like the future Lycone of the bulk point. So if you measure this experimentally, you will be amazed. What kind of, there's no boundary dynamics that can create a signal like this, because of the horizontal region in the middle. Okay. This particular event, we needed a particle, in order to make it look sharp like this, we needed to use energy of a few hundreds, which you would only actually achieve if you had if the tough coupling in ADS5 cross S5 was bigger than 10 to the 8. There's this thing in ADS safety that the string scale, the string mass goes like lambda to the 1/4. So you really need lambda big to have a big hierarchy of scales. Maybe this 10 to the 8 is a bit exaggerated, but okay, if lambda is very big, you could see some pictures like that. Maybe it's possible with smaller lambda. Okay, so let me finally there are some pictures to tell you how we measure the bulk distance. Because there's a few obvious ways you can measure bulk depth, right? So a very simple way to define this bulk depth, if I go back here, this is the future hyperboloid, but there's a past hyperboloid from which you're shooting. You can just ask like, what's the time separation between them? And that's like a back and forth time to this bulk point. And clearly that's a notion of depth. Very easy to define depth. What's the radial direction? There's various natural directions. Another one that I like is the parallax. So if the thing was coming out of the bulk point, and like a point that's like behind the screen and coming out, like when it comes here, it comes in at some angle, and when it comes here, it comes at a different angle, and that's what your eyes are using to like stereographically tell how far it is. You can do that here, and this change of the angle respect to position is like the curvature radius. The curvature of this hyperbola tells you the bulk depth. In ADS5 geometry, it's constant. Otherwise, it will vary a bit. We can do various ways. So you can see that, right, you, as I would describe, you can parameterize bulk points in various ways. Use in terms of a coordinate system that are like the shooting angles and position that you shoot. You can get a lot of boundary of coordinates in the bulk that are anchored at the bound. How do you read off the geometry? So first, let's see what these hyperbolas look like. So if you use different bulk point, this is what the hyperbolas look like in a, say, planar black hole. Okay. So this is a point very close to the boundary. You see the curvature is big, it's a radius close to the boundary. Then there's our points that are getting close to the black hole horizon. And what you're seeing here is that the shape of these curves no longer changes. The only thing that changes when your point approaches the horizon is that they get translated in time. That actually is the time that they increase, but not the parallax. So in some sense, the particle is not going further away from you, but it's just taking longer to get there, and that's 0 for the signature of a horizon. Not getting further, but it's taking longer to go. We can make this a bit more quantitative. So here's the recipe adapted from this earlier work for how you actually measure the bulk metric. So what you do is the following. It's a clever observation that, okay, let's think about the bulk metric is a function of tangent vectors in the bulk. So a tangent vector in the bulk is like a variation of this curve. So if this is a future-like cone of x, this is a future-like cone of x plus delta x. Okay? Now, there are some very special ways of choosing delta x, that if you use delta x that's along a light ray in the bulk, that's shooting toward the boundary, then there'll be a point on this curve that doesn't move. So whenever you have two curves that are slightly different, but are tangent to each other, you know that they differ by a null vector, null displacement in the bulk. And you can use that to reconstruct the bulk conformal metric. So it's very straightforward here. All you have to do is, so this is two curves that come from different shooting radius, shooting depth. And you see that what you have to ask is, how much do I have to translate this point in space and time that it becomes tangent to the other curve? That relates delta x, delta r, and delta t of a null vector. You do that here, and you learn that for parts, first you do it at the origin, it's very easy. At the origin, there's no delta x, there's just a delta t and delta z, and you learn that that give you the ratio of the dt square and dz square part of the metric in the bulk. Just from how much this displaced, how much time displacement there were at this point. And then just by looking at one other point on this curve, where now you know the dt square, you know the dx square, there's one of them you don't know, you can fix it from the other end. So just using 2 points on this curve, you fix all these metric coefficients up to overall scale. So you see it's usually redundant. You have an infinite number of points on this curve, but any 2 of them would give you the bulk conformal metric. In general, in D dimension, you need a finite number of points on the hyperboloid. Okay, how do you measure the scale factor? This is actually the easier part. It's just from the normalization of the amplitude that comes out. You can read it off from that. So basically all the information about the metric you get. So this is a bit different from reconstruction. This is really more like an experimental measurement. It's like an experimental protocol you could use to measure the metric in the bulk. And the thing which is I find interesting is that it's very over-constrained. There are many ways you could extract the metric coefficient. So in some sense, you have a check. So this is what you don't have in reconstruction framework, which are based on integrating equation of motion. You get an answer, but you have no way of knowing whether that's the right answer in any sense. But here, you can try to reconstruct the metric in many different ways. And if they all agree, then you can declare a vector. If they don't, then maybe there's no bulk metric in the state you're looking at. Yeah, we can play this game for small black holes. Yeah, we had some fun doing this. You can tell the radius of the photon sphere from the slope of these curves. I'm not going to go through that. Yeah, yeah, I'm basically done. I just wanted to exercise some work here, which is vaguely related to a paper that came out yesterday, but we studied two-point function. But if you study just on the right exterior of the black hole, if you like, this method would give you straightforward reconstruction of the exterior metric of a black hole. Now, what we claim in this slide and is that if you do very detailed measurement and you apply the correct integral transform on the arcing radiation that comes out of the black hole and correlate it with something you send in, you can effectively measure something in the analytic continuation with geometry that will tell you that will allow you to similarly read off the whole geometry in the interior of the black hole, or at least some analytic continuation of exterior geometry. And the price you have to pay is that you're basically using subtle correlations between arcing quanta that are suppressed by half a Boltzmann factor. So if you're willing to pay this price, you can measure the interior. If you only care about the exterior, you don't have to pay a price.
E is the inertial one.
It's the energy of the waves you send in, which physically is related to the resolution you can have in the book. E is the energy with respect to the Killing vector.
It's in some kind of teleportation because there were similar factors.
Yeah, I think you can do variants of this if you actually had access to a two-sided correlations on an external black hole.
Okay, yeah.
Then these factors may have some interpolation in terms of teleportation. But here they're just somehow small correlations between arcing radiation that comes out versus things you send in. Okay, if you were doing actual two-sided measurements, this might be related to some teleportation.
This is kind of like using Richelieu or something. Like you're using the fact that the Hawking quanta on the left are entangled with the Hawking quanta on the right. And that's the amplitude, the entanglement.
Yeah.
We're applying projection operators. So it's not a measurement, so you're projecting and then measuring something.
I mean, there may be variants that look like what you say. The thing we're thinking about here is not a projection operator, it's really a straightforward expectation value. But you pay this price from doing some kind of Fourier transform future. So you have to dig some exponentially small part of the signal. It's yeah, I think we're going to get it backward. We can discuss. So this is summary in some direction. Yeah. So we studied some boundary correlation functions integrated against wave packet. So it's really an exercise in geometric optics, but I hope it's entertaining. And yeah, basically we can use features that along light cones to read off about geometry. And our concrete result there of this paper is a factorization formula that tells you that combines exact solution of wave equation near the ADS boundary, WKB approximation on geodesics, and a flat space scattering amplitude. Combine all these ingredients into one formula. And I think there's some very interesting question that we're hoping to answer with this. So one of the reasons we wanted to do this for spinning particles is that if you put the stress tensor at the boundary, it becomes the graviton in the bulk. And I think one of the schematic thing that people have been saying since the early days of ADS-CFT is that, okay, the fact that gravity is gauge theory in the bulk must be related to conservation of the stress tensor at the boundary. So in particular, like the fact that all the bulk points are physically equivalent to each other, the equivalence principle must be related to conservation of T mu at the boundary, and like this, we're hoping to make this more precise, to really derive this form of the equivalence principle from CFT. Yeah, we can ask if we localize in ADS5, but how about ADS5 cross S5? How do we localize there? a whole bunch of generalization there. Yeah, the formula we describe ignores interactions that we know exist in the bulk, but the hope is that they don't affect too much the amplitudes we're describing. The hope is that we can actually account for that. Some framework, but this hasn't been done yet. So yeah, thanks for your attention.
Thank you for the nice talk. So the fact that you can get metric with different experiments and it's over constrained, you use that to get some consistency conditions on the endpoint functions of the CFD for these wave packets for holographic ones. Say that as Einstein gravity.
It is a consistency condition on like the peaks and some the thing that is hard to something we've been struggling with is that in order to turn this into some this one like kind of linear programming type things, we would like this constraint to be linear in a 4-point function. And but all the analysis I described was like very linear. Like you look at 4-point function for various external momenta, then you make a curve about where it's peaked, and then you talk about properties of this curve. It's very hard to state this as a linear property of the 4-point correlation function. So if that could be clarified, it would be really helpful. But yeah, exactly. That's the idea, is that it's massively over constrained, so this should and the 4-point, yeah, should tell something interesting about the 4-point function.
So if I move in the conformal manifold on the CFD side, or like in the modular space side, and so the higher derivative terms become more important, so bulk becomes fuzzy. What would that mean in terms of these 4-point functions?
Yeah, that's a good question. And this I don't have enough time to spend on this, but what happens is that if you try to make such curve, I discussed them in the earlier paper I for the bulk 2 years ago. If you try to make such curve in the theory that, for example, that the tail coupling that is smaller. So if you move in the moduli space, and the theory becomes less orthographic. What the delta gap, the higher spin gap becomes small. What will happen is that this picture will get blurred. And why does it matter? It's because when this picture becomes too blurred, you can't tell it apart from the future icon of a boundary point. And when the future becomes just the future icon of a boundary point, there's no information in it. This is single, this is bulk physics. So the information in this picture is the fact that this is curved at the bottom. So you lose that when the higher spin gap becomes too small.
So I have a question, is that, so when you really do this experiment and localize to some bulk points, I expect some factorization happens, that there's a universal Hart scattering piece that is just flat-based amplitude, and some other piece that depends maybe on the details of the metric. But so in this case, shouldn't there be a particular function that you can define to directly detect the metric rather than looking at the whole point amplitudes?
I'm not sure I understand what you said, but that sounds great. To discuss that.
Well, we thank Simon again for a nice talk. I'll remind you that we're going to dinner. Please send me an email before I can make a reservation. Thank you.